Hey everyone, after last lecture we introduced a whole bunch of ideas and I've kind of sketched them out here, or put the theorems here anyway. We talked about the idea of absolute convergence. A series is absolutely convergent if the sum of the positive pieces in the terms converge. And then we talked about how anything that's absolutely convergent will automatically converge, and so that's a powerful test. But if it's not absolutely convergent, then we might want to look at the alternating series test, which allows us to determine whether it's actually convergent in its own right. In other words, whether the sum of the a sub n's actually converges or not. And then we had the idea of things that therefore were conditionally convergent, which means they converge. So, for example, they satisfy the alternating series test criteria and the test decides that they converge, but they're not absolutely convergent. So these ideas all fit together, and we're going to do a few more examples today where we use them. Then we're going to look at sort of the size of the series, because so far we've been talking about whether a series converges or not. So we're going to spend a little time talking about what it actually converges to, or at least estimating that, because that's a hard problem. And then we'll end by talking about the importance of conditional convergence as opposed to absolute convergence, because these are very different series that are absolutely as opposed to conditionally convergent are very different. So let's get into our first example. Okay, so we've got a series here and we want to know which of the three options is the case here. Is this series conditionally convergent? In other words, does the sum of the a sub n itself converge? Is it absolutely convergent, which means does the sum of the a sub n's absolute values converges? And remember, we've got a theorem that says if that's true, then the series itself converges. And then the last question is, well, maybe it just diverges. So it's possible to be conditionally convergent, which means the series itself converges, but not the absolute values, or it could just diverge. So let's ask first about absolute convergence. That's the stronger of the criteria, because if this series is absolutely convergent, then the series itself is convergent and we're done. And so the sum of the absolute values here from n equals 1 to infinity is just the sum of this, 2n over n squared plus 1. Right? And that's because the individual terms in the original series look like this, and the absolute value of those terms just removes the minus 1s. So these terms in this sequence, if I were to write it out, the first one would be 2 over 2, which is just 1. The next term, this is the sequence a sub n. So when I plug in n equals 1 to the absolute value, so this is the sequence of the absolute value of a sub n, I'll get 2 over 2. When I plug in n equals 2, I'll get 4 over 5. When I plug n equals 3, I'll get 6 over 10, and so on. So that's the sequence. I build the series of absolute values by adding those all up. So we want to know whether this converges or diverges. And one way to approach it is to notice that 2n divided by n squared plus 1, that's actually going to be smaller than 2n over n squared, right? And that's just 2 over n. Is that helpful? Right? If I forget the 2 for a moment, because the 2's just here as a multiplying factor, and so in the end of the day it doesn't enter into our considerations, is this helpful? We know that n over n squared plus 1 is smaller than 1 over n. Well, what do we know about 1 over n? We know the sum of 1 over n diverges, because that's the geometric series. And these numbers are smaller. So this is no help, because we've got some numbers we're adding together, right? We're adding together the sum of the a sub n, and we know that each term we're adding together here is smaller than the corresponding 1 over n. But the fact this goes off to infinity, the fact that I've got something smaller, doesn't tell me that it converges or it diverges. So we have to do something else. So what I'm doing here is thinking about the direct comparison test from the previous section. That didn't help, so now let's look at the limit comparison test. And this is the way we usually go through it. The direct comparison test is easy if the comparison works. Otherwise, think about the limit comparison test. So if we're going to think about the limit comparison test, we need a sequence to compare with. So the sequence we're going to take is what this behaves like when n is large. Well, when n is large, this is a lot like 2n over n squared, right? And so that's equal to, because the adding 1 doesn't matter if n's quite large. And so that's like 2 over n. And that's, related to 1 over n. So the comparison I'm going to make is with the series that you get by adding up 1 over n. In other words, it's with the harmonic series. And the only condition for the limit comparison test is that all the terms that we're looking at are positive. Clearly these are positive because we take the absolute values, and 1 over n is always positive if n is bigger than 0. So this is definitely true. It meets the criteria of our limit comparison test, and so all we need to do is think about the limit of the ratio of those two terms, right? A sub n over b sub n, which, if you remember, is useful to write it as a sub n multiplied by the other term is 1 over b sub n, so I take the reciprocal of that, and we end up with a very simple limit to calculate. And we can do that in using L'Hopital's rule, or we can do that in the Calc 1 way. If we use L'Hopital's rule, we really need to change to a continuous variable x instead of a discrete variable n, and in this case we've got an indeterminate form which is of the type infinity over infinity, and so we can go ahead and differentiate, right? And we differentiate, and that leaves us something that is still indeterminate, but we can just cancel the x's and we're left with 4 over 2, and obviously that's just 2 in the limit, and so this limit converges to 2. It's bigger than 0, and so what we know is that the sum of the absolute values of the a sub n and the sum of the sum of the b sub n either both converge or both diverge together. If this is a positive number, or if this is a non-zero number, if it's bigger than 0, it's positive, these two things are positive, then the limit comparison test says the two series converge or diverge together. So we know the harmonic series diverges, right? The sum of the b sub n is just the sum of 1 over n, where n equals 1 to infinity. We know that diverges, it's the harmonic series. So by the limit comparison test, we know that the series that we're interested in there, well, the absolute value of the a sub n, we know that series diverges. So we got to this conclusion by resorting to the stuff from the previous section, because we were looking at the series of positive terms, and that's exactly what the previous section was about. So we know that the sum of the a sub n diverges, and so we know that the original series is not absolutely convergent, right? Because the sum of the absolute values of the a sub n diverge. Now the question is, what is this itself? Is it convergent or not? If this sequence itself converges, then we've got a sequence which is conditionally convergent. But if it diverges, then we've just got a sequence which diverges. So let's turn back to the original series. It's an alternating series, so the natural thing is to use the alternating series test to see if it actually converges itself, because we don't really have anything else to work with. So what we need to do is find another series which has the positive parts. So in other words, if I think about this, we usually use B, but seeing as I've already used B in this problem, I'm going to call it C. So C sub n is are the terms you get from just the positive series, right? N squared plus 1. So that's f of n. Now the idea here is we have some conditions we've got to show that this satisfies. Namely that these C sub n beasts should be positive, they should be decreasing, and the limit should be 0. So I'm just going to say these are clearly greater than 0 when n's bigger than 1, right? Because on the top you've just got 2n, so if n's bigger than 1 it's going to be positive, the bottom's always positive. And so what we're going to worry about is whether it's decreasing or not. So I'm going to think about the function f of x, which is the corresponding continuous function, and then we're going to take its derivative. So the derivative of this we calculate using the quotient rule, and we end up with something like this. And we want this to be negative. So the question is, when is 1 minus x squared less than 0? And the question is, and the answer is, well, when x squared is bigger than 1. And that happens, if you think about solving this inequality, that happens between minus infinity and minus 1, and then again from 1 to infinity. So this is definitely bigger than 0 on this region, right? When x is between minus infinity and minus 1, and from 1 to infinity. When x is 0, this is a positive number, but if x is bigger than 1, this is negative. That's what we care about. So f is a decreasing function when x is bigger than 1. That's the part we're interested in. And that tells us that this sequence of numbers, the c sub n, they decrease for all x bigger than 1. And that's all we needed, right? The last thing we need to show here, so we've got 3 things we need to show. We need to show that this thing is positive, we need to show it's decreasing, and we need to look at the limit as n tends to infinity of these terms, the positive pieces of the series. And that limit is going to be 0, because we can divide top and bottom by n, so we get 2 over n plus 1 over n, and in the limit here, this goes to 0, and we're left with something that overall is just going to 0. And so we've satisfied the three requirements of the alternating series test. Firstly, the terms are positive. Secondly, the terms are decreasing. And thirdly, the limit of the terms goes to 0. And because of that, we can say that the original alternating series up here is convergent. In other words, just summarizing, by the alternating series test, this is a convergent series. And to answer the original question, this series is conditionally convergent. It's not absolutely convergent, and so it must be conditionally convergent, since it does converge, but it doesn't converge absolutely. That's what we're looking for a conditionally convergent series. All right, so that was a long one, but the point of that exercise is it took us through all the pieces we have, and it's used the ideas we've had from the last couple of sections, so make sure you know what's going on with that one. Don't be misled by the web work. Some of the questions just say, does this series converge or does it diverge? This is what you should do for every one of those questions, right? When you sit down to work out whether things converge or diverge or are absolutely or conditionally convergent, you need to be working through all of these things, deciding how the tests apply and applying them. Because when it comes to a test, there's no points for the answer. All the points are for how you got to the answer. I want to spend a bit of time talking about a different issue, and that is the idea of the size of the actual series. So we're talking, this corollary here that talks about a positive decreasing sequence that converges to 0. That means all the terms are positive, right? B sub n is decreasing, and the values are actually going to 0. And that makes that original series, so by the alternating series test, right? That's the conditions for the alternating series test. So it's telling us by the alternating series test, when I add up these terms, I'm going to get a convergent series. So I've got a series that converges to something. I've met the conditions of the alternating series test here, and this is going to add up to some value. And the point is, whatever the value is, if it's convergent, what it means is it adds up to a finite value, and I'm going to call that S. So what this theorem is telling us is that the difference between the final value of the sum and the nth partial sum is less than the first term we're ignoring. So let's spell that out, right? Here's the nth partial sum. I'm adding up this alternating series, so it's b1 minus b2 plus b3. All the b's are positive. You know, this is what we usually call a sub n. They just haven't used that notation here. But the b's are the positive numbers, and I'm adding and then subtracting, adding and subtracting, because it's an alternating series. And the last one is added or subtracted depending on what n is, right? If I were to stop at b3, then I'm adding the last one. But if I stopped at b4, then I'm subtracting the last one. So that's what this piece is for. So that's the nth partial sum. But compare that to the entire series, which is where that idea goes on forever. You take b1, you subtract b2, and you add b3, and you subtract b4, but you never stop. So that's the total series. So what this is telling us is the difference between those is smaller than the first positive term we ignored, right? The next term that I ignored when I built the nth partial sum, the next term I ignored was b sub n plus 1. That's the one that would have come there. So what this is telling us is that first term that I ignored when I built the nth partial sum, that number is a bound on the error. So the difference between the nth partial sum and S itself, the total sum, is no bigger than the first term I ignored, the positive piece of the first term I ignored. Let's do an example and see how that works. So here's a series that we know is convergent. This series is absolutely convergent. Just quick note, since it's the sum of 1 over n squared, which is a p-series. And a p-series with p bigger than 1 converges. So the absolute value of these terms, of the a sub n, so here's our a sub n, the absolute value of the a sub n is just that standard series 1 over n squared that we started talking about. That's a p-series, it's convergent. Because the series is absolutely convergent, we know that this series must therefore converge. So by the theorem we had earlier in this section, we know that this alternating series actually converges all by itself. So we have a convergent series, which means it's an alternating series which converges, which means it satisfies this, right? As soon as we've got this detail just says that we've met the criteria of the alternating series test to have a converging alternating series. So as long as our alternating series converges, this inequality will hold true. So let's apply the inequality. We know what S sub 3 is. S sub 3 is the third partial sum, so it's 1 minus 1/4 plus 1/9. And the third partial sum is 31 over 36, or it's about 0.8611 recurring. Right, this 1 continues forever. So we've got the third partial sum. How good an approximation is it? Well, we know from our inequality that S minus S sub 3 is going to be smaller than B sub 4. Well, what was B? B sub n is the positive part. So B sub n was 1 over n squared. So B sub 4 is going to be 1 over 4 squared. So we know the difference between S and S3 is going to be less than 1 over 16. So the maximum error is 1/16. We can rewrite this as S minus S3 is going to be between a 16th and a negative 16th. That's what that inequality means, right? The absolute value. So I'm either a 16th, less than a 16th in the positive direction or the negative direction. And another way of saying that is S is between S3 minus 1/16th, whatever S3 is, and S3 plus 1/16th. And so just going on the next page to make a bit more room, what we've seen is S, this is the total sum, right? This is the sum from 1 to infinity of this alternating series. So this is adding up an infinite number of values. That's the key here. What we want to know is adding up an infinite number of values, and we've only added up 3. So we can say that S is between this number plus 1/16th and that number minus 1/16th. And 1/16th is about 0.0625. In fact, that's exactly what it is. So when I add them together, we've got a limit on the value that this total sum is. When I add up this total sum, what I find is a number between, well, pretty close to 0.80 and 0.9234, whatever that value is. So I know that my value for the total sum is going to lie between those. But of course, we could use more than just 3 numbers. So let's do the second part, and that used, I think, 5 numbers. So we were going to use S5, which is literally the sum of the first 5 values. And when I add those up, I get something like 0.838611. All right, and then our idea here is, again, S sub 5 is going to be at most a distance of B sub 6 away from the actual final sum. And B sub 6 in this case is 1 over 6 squared, because remember B sub n is just 1 over n squared. And so putting that together, this is 1/36. So that tells us that S is between S sub 5 plus 1/36 and S sub 5 minus 1/36. Just undoing that inequality here and rewriting it. And finding values for those things, we get a better estimate for S. And plugging in values for that, we find that the value of S is now, well, we've got a tighter one. Last time we said it was between about 0.799 really and 0.924. Well, now we know it's between 0.81 and 0.87. So we're really narrowing in. And as we add more terms, right, we're talking about if you add an infinite number of terms, you get some value. Well, as we add more terms, we're obviously going to get a better approximation because it converges to something. And so now we've got a way of quantifying the error here. So the error in this case is at most 1/36, right? Whatever that number is, because that's how much I'm adding and subtracting from each side. In this case, the error was at most 1/16 was our error term, because that's how much we were adding and subtracting from each side. So we've seen that if we take the first 3 terms, our error can be as large as 0.06. If we take the first 5 terms, the error goes down to 0.028-ish. Let's ask the next question, which is, what about if we want a really good answer? What about if we want an error of at most 1 in 1,000, so 0.001? Well, we know that this is the condition we want. And so here's the error, right? In our case, B sub n is 1 over n squared. And we want 1 over n squared, we want that error to be at most 1 over 1,000, right? Because we want the maximum error. This is the largest error we want. So 1 over n squared could be smaller than that, but it's at worst case this. And so we just solve for n. So we rearrange this. I can put 1,000 on the left and I put n squared on the right. They're both positive numbers. So n squared's got to be bigger than 1,000. And so n's got to be bigger than, I can take the square root here, the square root of 1,000, which is about 32.6 something, right? This is just 10 root 10. So our n value has to be bigger than that. So how many terms do we need? And the answer is we need at least 33 terms. N equals 33 terms. So if we want our answer to be accurate to 0.001, when we do this, we need to use the first 33 terms in the series, and then we can calculate our value to the error level that we want. And why do I want 33? Because 32 ain't enough. You can't have 32 and a half terms. You've got to have an integer number of terms. So I've got to have more than 32.6 terms, and that means the smallest number above that, that's a positive integer, is 33. So that's the minimum number of terms to get an error below this. So this gives you an idea how the error can be used. Before I go, I'm going to show you one last cool thing about conditional convergence. All right, I'm going to talk a little about rearrangements here. We know this series. This is the alternating harmonic series, if you like. That's what I talked about in the last lecture. We know the absolute value of that series is going to be divergent because it's the harmonic series, p series with p equals 1. And so this is a conditionally convergent series because it converges by the alternating series test. We did it last time. It was our first example of the alternating series test, but it doesn't converge absolutely. So this is a conditionally convergent series, and a conditionally convergent series has strange properties. Let's think about this. I'm going to call the value that I get from adding this up to, I'm going to call it S, right? Because we know this has a value. The whole idea of convergence is I can add them up and I get a finite value. So I'm going to call that value S. And then I'm going to suppose that I can rearrange it. And what I'm going to do is take the numbers and their halves. So I'm going to take each of the odd numbers and half of that. So I'm going to take 1 and a half and I'm going to gather them together. And then I'm going to take the next even number. So I've dealt with the 1, I've dealt with the half, and I'm going to take the quarter. And then I'm going to get the next odd one. The next odd one is the third. So this is plus a third. And then I'm going to take half of that, which is the sixth. So I'm going to gather them together, all right? And I'm just ticking off here the ones that I've dealt with. So I've got the third and the sixth, and then I'm going to take the next even number, which is, I haven't even written it down, but it's 1/8, right? Because I've already got the half and the quarter and the sixth. So the next even number is 1/8. And then I'm going to add on the next odd one, which will be a fifth. Notice I've got everything so far, the 1, the half, the third, the quarter, the fifth now, and the sixth, and the eighth is there. Half of a fifth is a tenth, so I'm pulling that from the series. But then the next even one, we've got the 1/8 here. So the next even one is actually, I think, 1/12, right? And then the next term after that will be the 1/7, and double of that is 1/14. And then the next one after that will be, well, 1/14 is already dealt with, so I'll have a 1/16. And I'm going to keep doing this. And all I've done is just take the terms and rearrange them. Right? So this is the series S, right? This is the same series. I've just rearranged the terms. Well, now I'm going to simplify them because 1 minus a half, that's a half. Now I'm just going to copy the quarter and the 8th and the 12th and the 16th. Those ones are just getting written down again. But the ones in between, I'm going to calculate them what they are. Well, I'm taking away a half. So this is a third minus a sixth. In other words, 2/6 minus 1/6, which is 1/6, right? And this is a fifth, this is 2/10 minus 1/10, so this is plus a tenth. And then this one is 2/14 minus 1/14, so this leaves 1/14. And then that pattern continues. But notice what I've got here. This is a half minus a quarter plus a sixth minus an eighth plus a tenth. I can factor a half out of all of that. That will be fun. If I factor a half out of everything, this leaves 1. Halving this term leaves a quarter. Halving this leaves a third. Halving this leaves, that's a half when I halve it, and then a third, and then a half of 8 is a quarter, and then a half here gives us a fifth, and then the next one is a sixth, and then the next one is a seventh. Remember, all I'm doing is rearranging and then doing some algebra, and then keep going. Well, look at what I've got in the brackets here. What I've got in the brackets here is precisely the series that we started with. So we've got half of, well, what do we start with? We start with 1 minus a half plus a third. That's S. Look what I got. We started with S, and we rearranged it, and we ended up with a half of S. Convergence series are weird. This isn't possible, right? You can't have a number, whatever this adds up to, maybe it's 5. I can't have it also equaling 5 halves, 2 and a half. That's not possible. That's why conditionally convergent series are weird, because they're infinitely long, and depending on the order that you add them together, or add and subtract, you can get any value you want. You can rearrange them to get any value you want out of a conditionally convergent series. A series that's absolutely convergent will give you a finite value, and it doesn't matter what order you added the terms up in, you'll always get that same value. Absolutely convergent series are wonderful. Conditionally convergent series, you can add them up in different orders. Remember, we've got an infinite number of things here. We're adding them in different orders. This time I just added them in that natural order. This time I regrouped the terms so that every odd term was paired with the half of it. So the 1 over 1 and the 1 over 3 and the 1 over 5 and the 1 over 7. And then I just had the other ones hanging around. If I add them in exactly the order I've written it down here, I'll get half the value as I would if I just add them in this order that I've got it written in. And so that's just really weird behavior, right? You should be amazed by that, because this is just a list of numbers I'm adding together. And it's the weirdness is coming from the fact that we've got an infinite number of terms and the series is not absolutely convergent. So absolute convergence is actually really important because it prevents this kind of weird shit happening. I hope you've had a good day. Hope everything's going well. Come talk to me, give me a shout. I'll see you soon.